Okay, I guess we're starting. Hello, everybody. My name is Daniel Havey, and I'm the program manager for Windows Transport. And myself and my colleague, Andreas Hammerskjold from Two Pint Software, are here to tell you about all of the new and cool networking features in Windows Server 2016. So let me hand it off to my colleague.
Perfect. So we're going to talk about two things. One of them is, that's better. So we're going to talk about two things. Basically, one of the things is bandwidth, and the second thing is latency. So a lot of people think that things are slow just because they don't have enough bandwidth. But typically, it's more down to latency than it is to bandwidth. So this is what we're going to cover today. And everything that we kind of talk about is about the bandwidth. But primarily in the most things, especially the things that Daniel is going to cover, is about latency and why latency will make throughput even better. So if you divide up the slides that we have and in the sections, we'll talk quite a lot about LedBat++, because that will help with the bandwidth side. And a lot of the other areas will cover more around the actual latency and how new technologies can help around that. So why is it so complicated?
Yeah, why is it so complicated? I mean, on one side, we have a user with their Surface Pro, great machine, by the way. On the other side, we have a popular internet resource from a popular website, and the user wants it. So, I mean, what's the big deal? Just go get it. All right, well, that content lives on a server farm or a cloud somewhere. So we go ahead and go through the access point, we go through an ISP, and we drill a path through the internet, get the resource, and bring it back. Seems simple enough. The problem is, the internet's a really complicated place filled with many, many different kinds of devices. And the users millions of different users have all kinds of different devices who are all accessing the internet at the same time, drilling their own pass through and creating a time-variant, highly variable traffic conditions that change so frequently that the problem gets quite complicated. All right, so there are expected to be 75 billion devices connected to the internet by 2020. And now let's see if we can make this a little bit more simple. Let's see what's common on every internet-connected device. So what's common is these three layers of the stack: the session layer, the transport layer, and the networking layer. So those are the teams that I represent at Microsoft, and those are the things that I want to talk about. What's really cool about these three layers in the networking stack is that we're uniquely positioned to make your internet better. The reason is that every packet that travels through the internet that touches a Windows host goes through these three layers. So let's go ahead and drill in a little bit more, and let's see what happens. A user clicks on a URL. Okay, so they have a DNS request. This is going to take one or two or more RTTs. All right, we burned up one or two RTTs. Then we go to the TCP connection. So in order to establish a connection, we're going to do a three-way handshake. That's 1.5 more RTTs. Then we can begin to transfer data. The first data we're going to transfer is our TLS handshake, our TLS certificates. So that's 1 or 2 more RTTs. Now we can get our URL resource, and we're done, right? No. A typical web page contains 30 or more different resources. So we're going to have to repeat steps 1 through 4 until complete. And the user might be looking at this hourglass for a minute. So let's see what we can do about that. Let's take a look at the TCP portion, the actual internet connection. Okay, so we see the TCP state machine on one side, and it's quite complicated, but I'm just going to break this into the 3 parts of a TCP connection lifecycle. So we start with connection setup, where we initialize the connection resources. And that's that big chunk on top. You see the three-way handshake. That's 1.5 RTTs burned up right there. So at Windows, we think that what users want from us in this portion of the TCP lifecycle is to connect faster. Okay, connection's done, now we can begin data transfer. On the right-hand side, we have the typical TCP sawtooth that it uses when it's transferring data. The things that we want to worry about here, where we're transferring data, is we want to find the available capacity in the internet. And we want to use exactly that. We don't want to use less than the available capacity because that's wasteful. And we don't want to try and send more than the available capacity because the packets will drop immediately. Then we'll have to retransmit them and it'll take even longer. So we want to reduce the latency and loss. Okay, the final part is connection teardown. So the job of the teardown section of a TCP cycle, a life cycle, is to collect any stray packets and then release any connection resources. So what we need to do here is find a way to tear down faster. Okay, so we've kind of looked at all the users and we sort of set them into 3 buckets so that we could sort of understand what we need here. And those 3 buckets are end users, and we have IT professionals and data center professionals. So end users want instant gratification. I want my stuff and I want it now. So in order to do this, we need to reduce latency. IT professionals, they want better resource control, so they can have better network utilization. And data center professionals, they want better resource optimization because they have SLAs to meet. Cool. Okay, so before we get into all the cool new features and all the great stuff about Windows Server 2016, let me talk about the life cycle for a moment. So on the left-hand side, we have us, Microsoft's ecosystem and the platform teams, the internet protocols, the teams that I represent. And on the right-hand side, we have you, third-party industry partners, IT partners, ecosystems, app developers, you name it. Okay, so on our side, we have people building apps, then we have us. We're building Windows features, and we're pushing those into the ecosystem, making them available to you through releases and through flighting builds. On your side, you're developing apps, you're pushing them into the ecosystem, you're deploying systems, and so it's a beautiful thing. There's a synergy that works here. We're working together. Now, on our side, we have this deep domain knowledge and subject matter expertise about Windows and transport and all these things. And on your side, you have this in-depth topological and customer-facing knowledge and understanding. So we just got to talk. You know, between the two of us, we could take this information and put it together and make great things. With the information that you have, because you're in there with the customers, you know, you're in the trenches with them, you're looking at their face, you're breathing the same air as they are, you're hearing the things that make them unhappy, you're hearing the things that make them happy. And we need that information in order to guide our feature development. So we want communication. We'd like you to communicate that to us. And what we would like to communicate to you is the features that we're developing that are coming out in the next release so that you can get ready for them, you can build your apps to take advantage of them. And so let's talk about the communication. We have a few ways of communication here. The most important one that I think is our Windows networking blog. So every release, I write a blog post with all of the most important Windows networking features. And we'd like you to read that. We just created an email alias. We'd like you to join that. You're not going to get spammed. Once every release, I'll go ahead and write that networking blog, so I'll probably send it out to the email alias that's available, and you can read this. That way you don't have to watch the blog for 6 months. We do have a Facebook page, or a Facebook group. That's experimental, so we'll see how that works out. So far, so good. There's an early adopters program, technology adoption program, and this forum right here, Ignite. Okay, so let's talk about the cool new features. I'm going to keep the same 3 buckets, features for end users, IT pros, and data center professionals. So let's look at the end users. One of the coolest features that we have here is called H2. HTTP2. So that's making the internet faster, making the web a better place for everybody. TCP fast open, we're opening our connections faster and we're making the internet better. ICW10, fast connection teardown. receive window auto-tuning, and dead gateway detection. So I'm not going to keep on reading the list to you, but we have LEDBAT, which I think is really a cool feature. I think that's going to make enterprise a lot of money. And we'll be talking about that in detail. My colleague Andres has this really awesome demo that we're going to see. I'm really excited about that one. We have a bunch of features for IPv6 conversion and some diagnostics. Ooh. Also for data center professionals, some loss detection algorithms. And let's move right in here. Okay, so let's talk about HTTP 2. The problem that HTTP 2 solves was in HTTP 1.1. So in H1.1, what happened is there's a thing called head-of-line blocking. So you go and get an object, and you bring it back, and the browser can't render this yet because it's waiting for another object. Maybe it's waiting for a CSS, maybe it's waiting for a JavaScript, who knows what. But anyways, the user has to wait. This is a problem. So browser manufacturers recognized this problem, and what they did to try and alleviate it is they said, hey, let's open up 6 connections at a time. You can see the graph over there on the left-hand side. And if you press F12 in Edge and go to Network Dev Tools, you'll be able to get a graph of your very own, just like this one. So I did an animation that's a little bit easier to see. We've opened up 6 connections. We're bringing down 6 objects. Can I start rendering the page for the user? No. No, I'm waiting for a CSS. OK. So bring down 6 more. Can I start rendering yet? No, I'm waiting for a JavaScript. OK, whatever. All right, so I got my CSS. I got my JavaScript. I can start rendering. No, oh, wait, I'm waiting for an image. Well, here we go. OK, we got the image. Can I finish the page yet? No. OK, there we go. Now we can finally finish the page. Clearly, we needed to do something better than this. The other thing that happened is most websites are sharded across domains. So that just means that the content lives on many domains, maybe 10 or more. Now, if the browser can open up 6 connections to every domain, and I'm sharded across 10 domains, that's 60 TCP connections. As a subject matter expert in TCP, I can tell you that's way too many. You're going to cause packet loss and overload your access point, and it's going to take even longer. OK, so let's take a look at H2. There's an H1.1. He's going one at a time, one at a time, one at a time. OK. Then we opened up 6 connections. We already described that in detail. Here goes H2. All right, let's take a look at what it does. Well, it opened up 1 TCP connection, and it multiplexes as many streams as you want inside. None of them need to block. They don't need to wait for each other. So everything can download at the same time. That's pretty cool. OK, so I've been talking for a little while. How about we have a demo? Time for a demo? This is one of my favorites.
No, so you're not on screen.
Oh, OK.
I pressed it. I thought, no, that's me. No, that's you. Yeah, sorry.
Oh, OK. OK, so on one side, I have an object that's going to download with H1.1. And on the other side, I have an object that's going to download with H2.0. The object consists of 200 small images. And they're both exactly the same. The only difference is the web protocol that's being used. So how many people think that the H1.1 is going to be faster? Raise your hands. Let's take a vote. No, I don't see anybody out there. How about the 2.0? Anybody think the 2.0 is going to be faster? OK, OK. A lot of people. A lot of people reserve their opinion. I'm down with that. You know, the proof is in the seeing. So let's go ahead and see what happens here. When I hit this button right here, the 1.1 is going to start loading. Oh my gosh, that's slow. OK, let's look at that. Wow. Look at the difference. 0.31 seconds versus over 2 seconds. Hey, let me try that again. Maybe it was just an anomaly. Bam. Ooh, look at that. Can you feel the difference? I love this demo. OK, that was kind of a slow one. Let's try it again. Nice. Okay, so I'd like to go back to the slides, please. Nice. All right, so it's still an H1.1 world, but H2 is a reality. It's starting to be deployed. You're starting to see it on the web in some places. And in a major service across many device types in mobile and PC, we have seen 10 to 20% latency improvement in the 75th and 90th percentile. And you may say, hey, 10 to 20%, the image looked faster than that. Well, it was. So this is without unsharding the domain. It's without content rearrangement. You do content rearrangement, it'll be much, much more. One last thing before I stop talking about H2. This is important to know because the cipher suite negotiation is different than H1.1, and you could run into trouble if you don't follow recommended procedures. The way this works is the client sends a hello with a list of cipher suites that it understands. The server has its own list of cipher suites. The highest cipher suite in the list from the server that is also in the list from the client will be selected. We'll send back to the client a server hello with the selected cipher suite. Here's where we can get in trouble. Some browsers, not Edge, will actually reject the connection if they don't like the cipher suite. And the reason that this is done, the reason that the cipher suites are still there that are not acceptable to H2 is for compatibility with H1.1. Now, if you have a fresh install of Windows Server 2016 or Windows Server version 1709, the latest and greatest coming out shortly, the cipher suite order will be correct. You will not have a problem. But if you've upgraded from an R2 and the cipher suite list has been changed, you might run into this issue. So the key knowledge that you need to know, the list is right there in that KB link, is if you're going to rearrange the list of cipher suites, put the ones that work in the top, and then you'll never have a problem. Okay, so let's talk about caching. Caching is great. I love caching. Caching makes the internet faster, and that makes the world a better place. So there's three types of objects in caching. There's non-cacheable, there's cacheable, and there's immutable, which nobody is implementing, except for us. We recently implemented immutable. And the reason that we did that is because with cacheable objects, if the user clicks refresh, which a lot of people do, particularly on sites such as Facebook, then irregardless of whether it's cached, the object will be reloaded again. Now, some sites that we've talked to have said, you know, we have these images, and they are never going to change. Not in 100 years, not in 1,000. If the image ever changes, the version is embedded in the URL, and the URL will change. So this really and truly is immutable. We implemented immutable for this purpose, and I have another demo. Okay, so let's have a look at non-cacheable. So, oh wow, that's slow. I hate slow internet. My God, it's killing me. Jeez. Okay, so if I click it again, it's going to do it again. Okay, I can't take it. I have to move on. Here, cacheable. Let's get it in the cache. Cacheable. Come on. Oh my God, I'm going to click out. Jeez. Okay, here we go. It's cached. Yeah, fast. We just take it out of the cache, pop it up to the user. They've got their image. Great, life is good. But the refreshers, like myself, click refresh. Oh my gosh, it's doing it again. Okay, so let's go over to immutable. So I can't take the slow internet. Okay, here we go. The first download is going to hurt. Okay. Oh my gosh, wow. All right, we're done. I click it again. It's in the cache, pop it up to the user. Great. Got instant gratification. That's what users want. Put a smile on their face. Okay, now here's the refresh test. I'm going to hit that refresh button, and bam, it's immutable. We never go to the cache, or we never go to the server. We never check for freshness. This object is immutable. We always just take it out of the cache, pop it up to the user. Instant gratification. Love it. Okay, so let's go back. Can I go back to the slides, please? All right, so we've talked about the session layer and the HTTP stuff and caching, so let's get into the transport layer, my favorite. So we talked about the connection setup time. How do we reduce that connection setup time? Well, with TCP fast open, which just happens to be available in Windows Server 2016. Okay, so we're looking at another drawing of the connection startup sequence, and we start with a DNS query. So how do we make that faster? Well, we pre-resolve. Went from one or more RTTs to 0 RTTs, okay? DNS instant, it's no RTTs. Okay, how do we improve the TLS handshake? Well, we advance the slide. Okay, here we go. We use session resumption and false start. So the way this works is, if I've already talked to this server, this client has already talked to this server, we've established a certificate. We both have it. There's no need to go through all that nonsense again, so we just use the previous one. And so it takes no time at all. TCP fast open, okay. So that works on a similar principle. It uses a thing called the TCP fast open encrypted cookie. This isn't a browser cookie, this is a TCP fast open cookie. And the principle is, on the first communication with the server, I'm going to establish this encrypted cookie. We both have it. And then whenever I need to connect to this server again, which could be many times because the web page has so many objects on it, I don't need to do the three-way handshake. I don't need to spend that RTT and a half because we've already done it. You know I'm not a DDoSer, I'm not an attacker, I've got the cookie, so all I do is I send my synchronization packet, it's got the TCP fast open cookie in it, it's got the TLS session resumption in it, and it has my HTTP request, and hello. Bam. Data is flowing back in 1 RTT. It can even happen in 0 RTT, but we don't have time to get into that here. Okay, there we go. There's the TCP fast open cookie. All right, so once we have the initial congestion window, once we have the connection setup done, then we need to see how can we make this packet transfer happen faster. So what we've learned through 40 years of study on the internet between ourselves and our industry partners is that 98% of the objects transferred on the internet are 15 kilobytes or less. So we want to make sure that we can get that 15 kilobytes out the door on the server immediately. So we went ahead and we moved the initial congestion window. The amount of bytes that can be sent from a server as soon as the connection is established is controlled by a thing called the initial congestion window. We changed the initial congestion window from 4, that's 4 packets, to 10. So it can send 10 packets. 4 packets will give you 6 kilobytes, 10 packets will give you 15 kilobytes. So there's a graph right there that shows the progression. But let's go ahead and look at this one. How much time does it take to transfer 15 kilobytes? Well, with ICW4, it takes 3 RTTs. With ICW10, it takes 1. 3 times as fast for 98% of the transactions on the internet. Not bad. And then here we have a graph which shows a latency plot. The higher the bar is, the worse the latency is. And you can see as the ICW goes from low numbers, 3 over here, towards the right where they're smaller, it keeps going down till it hits a point. Then it goes back up. So this is the answer to a question you might have been asking yourself. Well, if ICW10 is better than ICW4, why not make it ICW20? Why not 100? Why not 1,000,000? Why not ICW infinity? Well, the reason is that complicated internet and the time variant traffic conditions. So the available capacity is really important to us. If I send more packets than there is available capacity, the excess packets will immediately be dropped. Now I'm going to get into retransmission timers. I'm going to have to retransmit the packets, and it's going to take even longer. So there's diminishing returns. With a lot of study, we've determined that most internet paths can handle 10. 4 is too small. So we're moving over to ICW10. Okay, well, we're talking about TCP windows. This one that's really important to me, the receive window auto-tuning upgrade. So your throughput is controlled by the size of your TCP window. So we went ahead and we upgraded our algorithm. We have an algorithm that auto-tunes the window size for you. And we upgraded that to give you greater latency or less latency and greater throughput. So I have, not a demo because the servers went down somewhere in France. I don't know what they're doing over there, but I have a video. Will I be able to start that? Can we start? Can I start that video? I guess not. Yeah?
Yeah.
Oh, it's running.
It's running.
Oh, okay. So on the left-hand side, you see the buffer limited case. On the right-hand side, you see the auto-tuned case. Now, if you'll notice, we're getting 151 megabits per second in the auto-tuned case. That's the capacity of the link. On the other side, we're getting much less, but it wasn't getting to its capacity. Now watch it run again. On the left-hand side, look, it's maxing out at 12.6 megabits. That's because it's window limited, and that's the maximum throughput for that window. Well, the maximum throughput is actually 151 megabits for that link. So the window size is way too small. It should have been tuned upwards. That's why the receive window auto-tuning is so important. You want to go ahead and use receive window auto-tuning all of the time. And if you think that you don't need to use it, and you want to do this yourself, you should probably rethink that. And if you rethink that and you still want to use it, get on that email alias and talk to me, and we'll talk about it. So make sure that you can do it properly. Okay. So we've gotten to now we're on the fast, we're on connection teardown. A TCP connection can take up to 20 seconds to tear down. Now this is by design, and I can't change it because there's a lot of applications out there. They're not necessarily legacy applications, although some of them are. There's new applications that rely on this behavior. They expect that 20 seconds. And if I change that, I'll break them all. Okay, so we're not going to change that because I'm not going to break the internet. I don't like that idea. But we can't wait 20 seconds. In all cases, it's unacceptably slow. So what we've done at the transport layer is we've provided for you to be able to send a signal from application land down to us. And if you tell us, look, I'm done with these connections, I don't want them anymore, I don't want to wait, we will tear them down right now. We won't wait 20 seconds, we won't wait 1 second, we'll tear them down right now, they'll be gone. All right. So gateway detection. Sometimes your gateway just stops working. Now this could be as simple as it's a Wi-Fi and I walked out of range, or I'm docking or I'm undocking, whatever the case. We don't know at the transport layer what caused this, but we do have the ability to know, hey, this gateway is not working anymore. So at the application layer, hopefully, we expect that you'll know what to do if the gateway has gone dead. So between the two of us, we can figure this whole thing out. So here's how we do it. We have our happy user with a brand new Surface Pro, and they have 4 connections going. Everything's great. All connections are making forward progress. Hey, this is awesome. Okay, so one of them stops making forward progress. And we look at this, we say, okay, well, the rest of them are making forward progress, so possibly this is just the server stopped working, one of the routers along the internet path that we drilled when we started this connection stopped working, whatever the case. All right, another one stopped making forward progress. Well, and then when we get to a significant percentage, the DGD algorithm says, okay, that's it. I think that this gateway is dead. We send a signal up to user land. Hey, there's a dead gateway here. You probably ought to do something about this. Now, you might have been asking, hey, how come you didn't wait till all of them stopped? The reason for that is some connections have very large RTTs. Now, you might look at this one and say, 4,000, no, that's impossible. Well, if you go through enough satellites and go to outer space and back enough times, it can take that long. In fact, when I used to work for Aerospace Corporation, we did exactly that, and that's where I got the example from. So on a connection like that, it could take me a very long time to determine that this thing is not making forward progress. That's why we don't wait for 100% of the connections. We just use a significant percentage. Okay, let's start talking about the stuff for IT professionals. LEDBAT, one of my favorites. So LEDBAT is about resource control. This is a bandwidth scavenger algorithm. And what it does is it finds unused bandwidth in the network and uses it. LEDBAT is awesome. LEDBAT never interferes with other flows. LEDBAT is sensitive to traffic on other machines or anywhere on the network. So let's take a look. Got a nice little picture here. We have the sending rate on the y-axis, and then we have time on the x-axis. And you can see, as the time progresses, the LEDBAT flow sees, oh, there is unused bandwidth on the network. I'm going to go ahead and utilize it. It utilizes all of the bandwidth, not just some of it. It utilizes all of it. It's cruising along. Some urgent TCP job comes along. LEDBAT senses that, backs off out of the way, and waits until it's done. When the urgent flow is done, LEDBAT senses the network and says, okay, let's go ahead and utilize all that bandwidth. All right, so some uses for this is it's good for traffic that's important but not urgent. Maybe it's a non-critical Windows OS update. Maybe it's a database synchronization. Anything that's not urgent, but it's important that it gets done as efficiently as possible. Okay, all right. So I used to teach university, so don't be afraid, university networking classes, so don't be afraid of the math. Just take a look at the things that are highlighted in yellow on the screen. And what you see there is W is the window size. We already know that that controls your throughput. And I'm going to prove to you right here that LEDBAT is ridiculously fast and that it will never, ever win a fight with another TCP flow. It will always lose and defer. So if you look at the equations here, the top one is TCP equilibrium. Okay, so that big fancy word just simply means TCP running flat out at its maximum speed. So we have TCP running at its maximum speed, and then LEDBAT. You can see the only difference in these equations is we've made the denominator larger. If you make the denominator larger, then the window size is going to be smaller. LEDBAT will never, ever win this fight. If there's another flow, it will always defer. And then if you take a look at these values here, you have the target delay, base delay. These are based on the RTT. So LEDBAT is fast. Within one RTT, it's out of the way. Within one RTT of the urgent flow being gone or there being bandwidth available, it's going to use it. Okay, so LEDBAT is an RFC. It's not like a Microsoft invention or anything. But what we did is we innovated upon that, and we made some improvements. We're in the process of doing something called ransing these improvements, making them royalty and disclosure free. The reason is we want others to not only use this, but we'd like people to innovate with us and share with the community. That's where we're going with LEDBAT. Okay. So with that, let me turn this over to my colleague, Andreas Hammarskjöld.
All right, perfect. Thank you so much. So what we're going to look at is basically how can we enable LEDBAT for the first case. And to understand how we do that, you have to use something called TCP templates. Who knows what a TCP template is? Not a single hand, I think, yeah. So I find myself working with a lot of these technologies from Microsoft where there's not a lot of documentation out there, so we're going to try to change this going forward. But it's basically a way to, when the TCP connection is made to a server, the server or the client basically looks into a list of templates and see one that applies, and then it will apply that to the connection. And that template will control a bunch of stuff. So you can do some net commands to control it, and you can use PowerShell. So we're going to look at a few PowerShell examples. So that's how you enable LEDBAT. And it will never change during the actual connection. So whatever is used at the time of the connection, that's what it's going to use. So if you want to change, you have to do a disconnect and then connect again. So when we look at the actual templates themselves, one of the settings that you can do is that you set a congestion provider for that. So the template will know that, hey, if things get busy, this is the algorithm that I'm going to use to actually apply to it, which is exactly what Daniel was showing. So without further ado, this is just copied from the TechNet forum, but there are more things coming here. So if we can switch to the demo. This is basically just what I'm going to show, so you got it for reference, since you can copy and paste out of the slides. Let's see if I press the right button. No.
No, that's my demo.
No. Audio, video, man.
Rats.
No, that's wrong. That's good. Here we go.
All right.
Perfect. So these are the PowerShell commandlets that we talked about. So if you want to know about an actual connection, you can run get net TCP connection, and then it lists like basically every connection that you got. So you can filter it down if you want to get more sense out of it. You filter to state established, and then it's a little hard because the screen resolution is too high. So I did a little bit while Daniel was talking. It basically just dumps out the applied setting for any connection that's in established state and shows, and the setting that's applied is basically a net TCP setting. So if I run that, I get a bunch of data back, but basically there are a bunch of settings that comes out of the box, and you can define them yourself. So if I wanted to change something for an actual setting, I would then define the setting name and what setting I want to change. So if you want to do things that, like play around with change condition providers, this is probably the way that you're going to do it. And then here's the key to it. You basically do a net or a new net TCP or net transport filter with the setting name, and then you define how it's going to apply. So I think I have on my server here. Like if I look at my filters that I have active, you can see I got automatic and the data center custom. And here I've actually given it a destination prefix. So if I do get my actually settings here. Yeah, so if I go and look at my data center custom settings, you can see that my congestion provider in this case is LEDBAT. Does that kind of give you an understanding what you can do with the templates? So you can define different settings. Typically, it's like Daniel says, don't change anything, because they do an extremely good job to do all of the math for you. So don't go and just change things because you can. I think one of the things that you might want to change is things like the congestion provider. Does that make sense? All right.
Makes sense to me.
Makes sense to me. Let's go back to the slides for a minute. Cool. So now when you know how to enable it, so you basically use your congestion provider, then you enable LedBat. There will be more stuff coming with the upcoming releases of Windows Server around managing this as well. But basically, why are we going to use it? Well, we're going to use it to make sure that we can get content out in a good way without disturbing the network. We want to protect all of the servers as well as the network from getting overloaded. So you can use the same technology both as a sender, sending things to servers, and downloading things from servers. But it basically also gives you an extremely good way of prioritizing traffic. So in the old days, this is what we had to do if we wanted some content out in an enterprise. We were given like 20 to 30% of the WAN usage. You can't use anymore, maybe a little bit more on the weekend, and that's what we had to stick to. And that was kind of okay until that day when something was really needed, and everybody had 20 to 30%, and the phones start ringing, and things are bad. How many gets a call when the networks is slow? Yeah, a few hands. Who's in here is like a config manager admin pushing software or patches out? Yeah, quite a few hands. So basically, then the phone rings. Why are you pushing stuff? Well, because we have to patch and we have to do, and well, and then point of sale system is much more important. Okay. So what LedBat gives you the ability to do, since it'll try to use as much bandwidth as it can, but it will always back down to any other traffic. So if you define it pretty well, you can then say that, hey, this content coming from these servers or these subnets or these ports should back down and not actually use as much bandwidth as you can, but if there's anything else, it will basically just back down. So we get a pretty good demo. This is one of these things as well as out of the box, it's very hard to show what is going on. So we're going to use one of our tools. We're going to release it for free. We had a bit of time to take all of the changes that we were doing to client systems and server systems out of it. But hopefully within a week or two, you should be able to download this as well and play around with it. But we got a client's going to do a download from a 2016 server that has LedBat. That's the one that I showed. And it will happily go along, and I think it's actually downloading as we speak. Then we're going to do an SMB transfer, basically copy a file from another server that's not LedBat enabled to my client. And I could have done an HTTP transfer from the same server, but on a different port, and depending on the context. But what's going to happen is that my HTTP transfer is going to back completely down. And I'm going to try to visualize what the server is actually doing with this. Does that make sense? All right, let's go back to the demo. All right, so if I'm lucky, the demo is running. So
wow, that's a really nice tool.
So what we're trying to visualize here in the background, you can see, it might be a little hard, but that's a bit better. I'll have to use the Control-4 live zoom. So what we're looking at is we have a remote address, which is the server that's sending the data. So we're actually getting events from the server as it's sending data. So it gets notified from the TCP IP stack that, hey, something's going on here, and the line seems to be busy, so we need to back off. So we're capturing all of these events and sending it up to a live dashboard so you can actually visualize it in real time. So as my client downloads it, the server keeps track of, oops. See, I'm not used to this zoom in. How do I get out? Oh. Lost my mouse too. This is what you don't want, right? Uh-oh.
Wow.
That's freaky.
That's awesome.
Where's Drasanovich when you need him? Huh?
He's the one that told us to use Zoom it, isn't he?
Oh, man.
Ooh.
Alt-V? Alt-Z?
Alt-Control-C?
Control-Z? No, it's not responding. I think it kind of crashed. Any other tips? No, escape. No, nothing. It's normally responding to this.
That's a good plan.
All right, let me see if I can get this.
But not till after the demo.
No. Oh, man. Well, we can switch back to the slides, and you can do, there's a little bit of the RFC stuff. So, meanwhile,
okay.
Meanwhile, I'll try
let's go ahead and switch back to the slides. And then you want to just go back?
Yeah.
All right.
I'll try to fix it out.
Okay, so LEDBAT is a congestion control algorithm, and I kind of like, I used to do kickboxing when I was much younger, and didn't get hurt so easily. But I like boxing analogies. So in a boxing analogy, LEDBAT is like a punching dummy. You just hit it once, pow, straight to the mat. Okay, so TCP cubic is the opposite of LEDBAT. It's more like a prize fighter. It's going to go the distance with you, and in the last round, it's going to try to knock you out. This congestion control algorithm has a reputation for being the most aggressive congestion control algorithm in the wild. Now, personally, I think that's not necessarily true. I think that it got that reputation because of the quiescence bug, which made it a lot more aggressive, and it's been fixed. So I don't think it's that aggressive, but still, I mean, it's definitely more aggressive than LEDBAT. So let's take a look.
We're back.
Ready to go?
Yeah.
All right, let me finish up the cubic slide, and
Yeah.
we'll backtrack. All right, so in a low bandwidth situation, cubic is going to be pretty much the same as regular TCP. When I say regular TCP, I'm talking about a thing called New Reno TCP. You can see the graph here. On the y-axis, we have bandwidth. The higher you go on the y-axis, the more bandwidth you have. On the x-axis, we have time. The further you go to the right on the time series, the more time it has taken. So we can see that regular TCP, that thin yellow line, is getting about the same amount of bandwidth as the cubic TCP, which is the thick orange line. And you'll notice it has that beautiful cubic curve that it was named for. That's the cubic congestion control window progression. Now let's take a look at a higher bandwidth situation. Okay, so look what cubic did. Oh my goodness. We see regular TCP is just kind of chugging along there, and cubic got to the higher bandwidth capacity much, much faster than poor little old New Reno. It got a lot more bandwidth. It's probably going to win this fight. So, uses for cubic: long-running urgent flows, critical Windows OS updates, security patches, that type of thing. You might ask, okay, if cubic is so great, why didn't we enable it by default? Well, the reason is we need to be careful. We have a really large footprint in Windows 10. I think 600 million machines out there. We could seriously break the internet if we did something without being careful. So cubic has been around for a few years. The quiescence bug has been fixed. It's been a few more years after that. We think it's okay. So we've enabled it. You can go ahead and turn it on right now in your Windows Server 2016. What we would like is for you guys to try it out, turn it on, test drive it, give us feedback through the email alias. Let us know what your experience was like, and based on what we hear from you, then we can decide, okay, maybe we should turn this on by default, or maybe we shouldn't. Okay, so let's
All right,
back to
cool.
the lead-bat demo.
Let's go
No
back.
more zoom it.
No more zooming. Yeah, I'm gonna stay away from zoom it from now. But basically, I use colors instead. So we got the blue donut. That shows us the base delay of the actual connection. So I'm using a simulated WAN with about 10 megabit, I think, with a base latency a little bit. And then I put my download on top of it. So it sees here that, hey, there's something going, but it's basically quite happy about it. So if you look at the green donut, what that basically symbolizes is anything above 0 means that it tries to speed up a little bit, or just test to see if there's room to push the boundaries. And anything below 0, so that will actually go to negative if this connection should be or is competing with something else. So then you could see, if you look at the yellow bar or the yellow line and the blue line dials, they're basically over time. So you can see it's trying to push a little bit. It's basically doing what TCP does. It's trying to actually get a little bit more data through, but it realized, hey, if I do this, things get busy. So, and if you look at my actual download, this is what I'm tracking. So we're about 950 megabyte. And let's see what happens if I put additional load on this line. So I have my very important data, and I'm going to copy it. So I'm copying it from another server that's not lead-bat enabled. So let's see what happens. So, like instantaneously, the green goes to red. So it knows that, hey, something else is actually downloading. And if you look at the download, you can see it's more or less stuck on 973, right above it. Might be a little small to see, but I don't dare to zoom in with zoom it. But you can see around here, it says 974. And this download is basically filling my entire pipe with content. And the other connection is just sitting there. It's not dropped, but it's basically only using bandwidth that's not interfering with the other connection. It's pretty cool, huh? Yay? So, and how fast is it? So if I basically go in here and I say, no, I don't want that. And the second you see the copying is going to go down, you'll see, bam, straight up to very extremely high, and it starts pushing data. And if you got glasses, you can read. You can see that we're at 980, 981, 982 megabyte download. So it's extremely fast to figure out. So the end users don't really need to know that there is some other load that you're putting on. But if you have free bandwidth, then why not use it? So. And then as this download goes, it will continue to just monitor this, and when other things go, it will say, hey, I need to wait for this other data to go through. So that's pretty much summarized the demo. So let's go back to the presentation.
Oh, that was a really great demo. Love that one.
If you don't use zoom it.
Oh, you're done?
Yeah.
Oh, okay, I thought you had some more slides. Okay, thanks for the awesome demo.
Yeah, I think or did you, yeah, maybe you, you clicked forward, didn't you?
Things.
Yeah.
That's what I thought.
Yeah, so this one, I think Daniel actually did cover a little bit. But it's basically, so the Microsoft version of lead-bat is different than the RFC lead-bat. I think it's a bit better because it doesn't, especially if you're doing peer-to-peer networking, and you have multiple hosts downloading the same file. What the regular lead-bat suffers from is that the people that come late to the game, they basically come in and compete with the other guy, so the other guys back off from that guy. And as long as, he basically trumps them down. So by measuring the RTTs and doing some other smart stuff, basically the start-stop behavior that you saw with the pink bar that kept going, it keeps track of the connection really well. And if you look at the two, like an example, if you look at the two diagrams, like the top orange one is we're trying to get across here. With the regular throttling, you were able to get 13.5 gig across a period of time using regular throttling at about 20% of the connection. If you use lead-bat, you'll be able to get 37 gig across the same connection.
Nice. Lead-bat wins.
Which is a pretty good way of actually, so this will enormously help with Windows 10 larger payloads for some of these feature updates to be able to get them out to distributed environments where the WAN link might not be good. So it's a pretty staggering increase of data. And at the same time, your regular throttling can be combined with this as well. So if you want to, you can actually use a combination of the regular throttling with lead-bat, and then the lead-bat throttling will make sure that if there isn't, you try to use 20% or 30% of the connection, but if there is some other traffic, it will back down. So a lot of when we talk to customers, a lot of the things we come across is like, yeah, this is all great, but how do we prove it? And how can I justify going to server 2016 on some of my distribution points, or a lot of edge servers that push content? I think one of them is tell them to go to conferences like this, attend sessions like this, or show them the actual data themselves. So our tools will be able to implement and to just show the actual numbers in your environment. So, and with that, I think I hand over to you.
All right. Thanks for a really great demo. I always love to see lead-bat in action. So, all right, let's get past Cubic. Okay, IPv6 readiness. So here's our IPv4 to IPv6 transition technology timeline. So at one point, a long, long time ago, there was an IPv4 only world. I don't know when that was, but it's in the past. At some point in the future, a long, long time from now, there will be an IPv6 only world, and I don't know when that is either. Okay, so in between these two extremes, we have a couple of milestones that are important. So the first types of technology that came out were tap and 6-to-4 technology. Oh my gosh, excuse me. So the reason we needed 6-to-4 technology is because we had an IPv4 world. Somebody comes along and builds an IPv6 app, and it's living on an IPv4 host. It can't communicate, so we needed the 6-to-4 technology. That's no longer the case. I am not aware of any stack that exists that's not capable of at least dual stack, or it's just plain v6 only. So we've disabled these technologies by default. They're still in the build, they're still available to you. If you want them or need them, you can turn them on. But
can we get a clap to that?
Yes, yes.
I lost 6 hours on my demo kit because IPv6 tunneling.
Everybody loves this tap in 6-to-4. Okay, so moving forward, we're moving towards that v6 only internet, and the next type of technology is 464 XLAT. So we think that the world is about here right now. So because of that, we've moved support to the desktop and tablet for that, only for cellular, not for LAN. And the reason is that there's a lot of new devices, tablets and convertibles, Surfaces and such. I don't know if the Surface is going to have cellular technology, but they have cellular and they have wireless. So we've brought this technology along. And we've done a couple of other things for IPv6 readiness. We now accept router advertisements to configure DNS. We prepare IPv6 flow labels, which some sites use. It's important technology for v6, but not necessarily important to you unless you're using it. If it is important to you, you probably already know what those things are, so I won't discuss them in detail. All right, we have improved our diagnostics. Now, we could look at this big orange slide, or I could do another demo. I say let's do the demo. Let's see, demo button. Ooh, that's not cool.
You can use testnet connection to figure out why why are you disconnected.
Oh, you're tormenting me. Oh, there we go. Okay.
Is it readable?
So,
Is it readable? Almost.
maybe. It's on the slide. So, okay, so we're going to use testnet connection. And here what I'm going to do is I'm going to go ahead and I'm going to make this fail due to a DNS error. So let's go ahead and run it. It's resolving the name, finding a route. Oh, okay, look. Oh, requires administrator. Yes, it does. That's kind of important. PowerShell. So now that we're running in PowerShell as administrator, let's go ahead and do that again. Ah, your DNS failed. That's what's wrong with this connection. So we consider this like our first line of defense. Now, this is enabling users to sort of figure out what's wrong with their connection themselves before they hit the feedback hub and report a bug with something that we can't decipher and we can't make any sense out of. So let's go ahead and let's fix that DNS error and let's see what's really cool about this thing. So what it's going to do is it's going to go ahead and parse all these routing events, and it's going to dig into the routing table, and it's going to tell you what routing decisions it made and why. This could be very useful information for our IT administrators. So there we go, right there. It's telling us why it did what it did, amongst other things. So that's one of the improvements that we have in diagnostics, and I would like to go back to the slides. Okay, TCP statistics. This goes right in there, fits right in there with diagnostics. So the old way of collecting TCP statistics was you have a bunch of TCP flows, and you want to look at a couple of them and get stats on them. So we would take stats from all of the flows, filter out the unwanted information, and then you could look at your stats. Clearly, oh, by the way, that also requires elevation because you'll be looking at other people's TCP flows. So clearly there's some problems here. First of all, what if you're not admin? Now you can't even look at your own flows. Secondly, on busy machines with really fast connections and lots of them, this is a lot of overhead. It can take a really long time. You get this thing running in a data center, oh my gosh. You collect a half a second's worth of data and it takes like multiple minutes to parse. So anyways, our solution to this is the new method of collecting stats. You throw a socket option and it only collects the stats on the flows that you're interested in. No elevation required, just go ahead and collect your stats. All right, so we're nearing the end. We just got a couple more features here. This is, these two features, tail loss probe and rack, are for better loss recovery. So what happens when a packet gets lost is we need to retransmit it. There's two ways to do this. Every time we send a packet at the transport layer, we start a timer. If that timer pops before I receive an acknowledgement, I'm going to retransmit the packet. So this is really good. I mean, it always works. But the problem is it's slow. It takes a really long time for that timer to pop, and then we can get into exponential back off, and it could be a very long time before you get your packet. So we have a faster method, and the faster method is by packet counting. This is called fast recovery. So if I'm missing an ACK and I receive an ACK for another packet, I count one, and I receive another packet, another ACK, and then a third ACK. When I get up to 3, I say, you know what? I think that packet's missing, so I retransmit it. Okay, this is a lot faster, but the problem with this is, what if it's the last packet that got lost? there's not going to be 3 more packets, so now we're going to have to wait for that RTO. This shouldn't be a big deal, we thought. This is back in the days when we thought, oh, okay, the internet consists of a bunch of TCP streams that open up, send a pile of data, and then close. Well, that's not what happens on the real internet. On the real internet, because of traffic conditions and the time variance and crossing traffic, what happens is there's bursts of packets. Many, many, many bursts of packets. So you have lots and lots of opportunities to lose one of those last packets, and then all of a sudden you're into this RTO, and it's slowing everything down. So we have a graph here which shows you what happens to flows, to the latency in flows that have packet loss. It's in the red cross-hatched histogram bars. And on this chart, higher is worse. Okay, so we look at that and we compare those to the green and blue flows. Those are ones without packet loss. And we can see there's quite a bit of difference here. So we want to get rid of that. What we want to do is we want to convert those RTOs into fast recoveries. And we do that with tail loss probe. What it does is it essentially uses time instead of packet counting. And it says, oh, you know, this packet's been missing for enough time. I think I should have got a knack back. So I'm going to go ahead and retransmit a packet anyways, just in case to find out. And the SAC will take care of the rest of it. The same with rack. Rack eliminates packet counting. Instead of counting packets, it uses time. So here's some of the improvements that have been measured. The maroon colored histogram bars are the 99th percentile, and the blue ones are average. You can see for various types of traffic, we're significantly decreasing the latency, which is one of our major goals. So we've implemented tail loss probe and rack. All right, single connection performance. Previously, Windows, the way to get faster throughput with Windows TCP was to go with parallel connections. Now with H2, and I already told you about parallel connections, and you get too many of them, they interfere with each other, you cause packet loss and all of these things. So now we're going towards a world where it's going to be single connections. We've increased our single connection performance in the new version of Windows Server 1709. Well, we can now push 26 gigabits, whereas before we used to push 14 gigabits. CPU is reduced, usage is reduced by 40% while we're doing that. And on the UDP side, we have 125% improvement over the previous Windows Server. For standard I/O sizes. For really small I/O sizes, which are hopefully never used, but I don't know, maybe there's someone out there using those things, it's actually 1,700% faster. So, okay, I've told you about all this stuff, but the proof is in the seeing. So let's go ahead and go to a demo, and hopefully that's still working, because it wasn't when I looked at it the last time, but we'll see what happens. Yes, today is my lucky day, sort of. Okay.
I would almost recommend you to use Summit, but I think I learned my lesson on that.
All right, so this is the new latest and greatest Windows Server. All right, so look at this. We're getting 14.2 gigabits per second previously. 28.9. I thought I saw 30. There's the 30.
32.
31 gigabits
32,
per second.
38.
Yeah, look at that. Yeah. Okay. So yeah, the new versions of Windows Server are much, much faster. This is just the first step in this journey. We're going to continue to make single connection more and more performant and faster. So I'd like to go back to the slides. And we are at the end of this presentation.
That's the email slide.
Oh, they put those in there.
Yeah.
Okay, so do we have any time left? Can we take questions?
I think we have 6 minutes.
6 minutes. Do we have any questions?
There's mics on the sides if you have any questions.
Okay, I have 2 questions.
Yes.
We've been doing a proof of concept project on using internet technologies for media rather than using UDP. So we've been using Windows Rio, and we've been looking at the use of BBR, which obviously is on Linux platform. The first question I have is, are you going to support BBR at any point?
Okay. I am not allowed to comment on future features in Windows. However, look, transports is a well-worn path. It's obvious, if you know about transports, what the right things to do are. And I can promise you that we're going to do the right things. We've started supporting more and more congestion control protocols. We've added LEDBAT. We've added Cubic. We still have Compound. I can't tell you that, yes, we're going to do that. All I can tell you is we're going to do the right thing for the internet.
Okay. Yeah. Well, the second question is Windows Rio. Do the changes you've made in 1709 make it redundant?
I'm sorry, I don't know what that product is.
Windows Rio, Windows Real-Time I/O, accelerating UDP.
Yeah, I don't know.
It's used in the financial industries for cutting down kernel latency, but we've been using it for media streaming.
Okay, so they're trying to accelerate the UDP, make it
I mean, it's
faster?
Microsoft. It is a Microsoft product. It's not.
I would say that it's probably going to work in conjunction with this. I mean, well, yeah. I mean, UDP is our baby, so I don't know. I don't know what they did.
And last question: would it be possible to get your details and link our software engineers, architect up with you guys?
Yeah.
They've been doing some cool things, and let's face it, this is one of the few products or projects in this arena that uses Windows.
Yeah.
Nice. Yeah, absolutely. The email alias will get right to me, and I would love to work with you guys.
Okay.
I wasn't kidding when I said I wanted to hear from you.
Yeah. All of the contact details is in the slide, so you can get it from there.
Thank you.
Perfect.
Hi, can you speak to any improvements made in the PGM layer of the PGM multicasting, reliable multicasting?
Ooh.
No, I cannot. As far as I know, we have not done anything in transports.
Why do you want to multicast?
Personally, I have to update about 500 servers with about 120 gig, and it's hard to do.
But you would probably get a more reliable result using an up-to-date peer-to-peer platform to do that than using multicast. Multicast always drops. I mean, even if you drop like 2% of the stuff that you want to send, the headache to manually, fix that, which is typically what you have to do, is really painful. So we do a lot of removing multicast solutions and replacing it with peer-to-peer from the client side. And we can talk like thousands of machines in the same subnets using enormous payloads as well. Like some of the biggest ones are like 44 gigs going to thousands of machines. And the results are more or less 100%. And they are often a lot faster as well. What kind of throughputs do you get on the multicast?
Well, that's the problem. I mean, the network it's not one level network. It's a network made up of some very fast links and some very slow links. Yeah. But yet these servers have to stay in sync, in balance.
I would go peer-to-peer. You'll get better throughput and better results.
Thank you.
Okay. So, you should get on the email alias. I would love to have this discussion with you. And as a matter of fact, it just so happens that my advisor's PhD project was multicast, so I feel kind of embarrassed. I probably should know more about that. But look, man, if there's a product that really needs to be in Windows, we're going to build it. So let's talk.
You were next.
Yep.
Yes.
No, he was next.
In regards to using the templates and enabling lead-bad, is there maybe a white paper that would give some best practices or scenarios where you use that? For example, like the network between Hyper-V and scaled-out file servers, so forth and so on?
Yeah, so the API is being built, for lead-bad is being built right now as we speak. That's going to go into the next release, and the Windows networking blog has information on how to use all these products.
Okay. Yeah, but it's a good comment. We'll take that with us to write up. Is it especially on the server side you want to know?
Yeah, just server side, or you know, just different scenarios within an environment where you might use or not use these enhancements. Yep. Nope. Thank
Also, the email alias. That would be a great place for a discussion about these type of things.
I just have a quick question. That was loud, sorry. About lead-bat and qubit. Are they limited to subnets, like, or in IP addresses as far as where it's utilized, or can you drill down and say, all right, this server to this server, but only certain ports or protocols? Or?
Can we switch to the demo machine, my machine?
Yeah, the API for a lead-bad is not complete yet, so I can't comment on exactly how it looks. Although we would love to hear your needs and opinions on the email alias. However, Andreas has some TCP template wizardry that works right now.
So these are basically you define it in your destination prefix, which is no, sorry,
it's still on my demo.
Yeah. So you can do quite a lot of smart things. You can use the remote port, you can use the local port, you can also define it per subnet base, and you can do it per server as well. So there's quite a lot of things that you can do today. So you can also stage your content that you want to push faster on one server, and don't use lead-bad on that, and the other one you use lead-bad on. So then you send like packages or data that it's okay to take time, you put that on the lead-bad server if you don't want to define, and you just enable that for the entire server, and then you use the other server for more content that like you want to push. So there's plenty of ways to control it. So, you're welcome.
Hello. I have a primary DNS server and a secondary DNS server. If my primary DNS server for some reason stops, my understanding is that it's a timeout before the secondary DNS server is detected. And the timeout is quite long. Is it any plan to improve this
That's
algorithm?
a really good question.
Yeah, that's an excellent question. However, I do not have the answer to that because DNS is owned by our sister team, the HTTP team. Email alias. And I could get the information from the people that build it. Yeah. That is a good question.
A quick one.
Yes, sir.
This improvement with lead-bat, etc., could, let's say, it's been said to improve the bandwidth and let's say how the traffic can flow. Microsoft produced a bunch of protocols and either from delivery optimization, bits, and all this kind of protocol and traffic just to improve, let's say, the load balancing and improve the transfer. Is there some kind of synergy between your different teams in order just to sense, let's say, which kind of, let's say, for example, that technology can be also mixed with these?
Absolutely, absolutely. We're working with teams across Microsoft to implement lead-bat. The cool thing about lead-bat is it's a transport protocol congestion control algorithm, so it can be used in conjunction with anything that you use TCP with.
Yeah, but in particular, when you're talking about the fact customizing, let's say, between what the thing should take place, rather than having some kind of static scheme like what we're doing now, if it's combined with
so what you're seeing,
a tool.
what you're seeing here in the PowerShell and the templates is that's the initial step on this journey. As other high-level like tools will start using this, they will probably implement their own ways for you to enable it. So, but they're not.
So is it something started, or if it's not yet?
Yeah, the API is being the first step in the API journey is being taken as we speak. It should be going into the flighting builds within a week or two. And it's just the first step. I mean, the more that we hear from you guys, the more that we will direct that into our products. And I realize that, you know, just the first simple API is not going to be sufficient for all scenarios. So clearly we're going to have to work on that. And we would really appreciate your input.
Thank you.
On that journey. Mm-hmm. Yes, actually, that's awesome. Marcus is from the delivery optimization team.
Can you repeat for the recording?
Huh?
Can you repeat for the recording? Can you repeat?
Can I repeat what she said?
Yeah.
Word for word? No, no.
No, but in high level. High level.
Oh, okay. Short-term memory, sorry.
I was saying that delivery optimization is looking at its own upload traffic as low priority traffic. And so the way we're thinking of LEDBAT, using LEDBAT is to throttle back the DO upload traffic if there's more critical traffic that's happening now and needs the bandwidth. And so this is how we're going to basically adjust to congestion on a network, kind of throttle back, and then go and upload again when we can.
Yeah, awesome. Yeah, Marcus has been a really great partner team in the LEDBAT journey. And so our vision for LEDBAT is, look, every Windows update that's not a critical security patch on the planet should probably use LEDBAT. And how we're going to make that happen, well, we'll see as we continue on this journey. So the first step is we built LEDBAT, we've got it into the product, we're using it on DO uploads, we're getting ready to use it in other various cases, and so that's where we're going with it. Whatever we need to do in order to get from here to there, we're going to do it, because we're here to do the right thing for the internet and the world. So.
How does this affect the devices, like the routers, the switches, and other, other existing hardware that you already have? Are they going to have to become this LEDBAT compliant?
No. No, LEDBAT is a congestion control protocol. It's just like any other TCP congestion control protocol, and the middle boxes are not only not aware of it, but they have nothing to do with it. All LEDBAT does is it affects how many packets TCP sends per RTT, the same as any other congestion control protocol.
So it wouldn't create any kind of saturation problem or anything?
LEDBAT will not create a saturation problem.
That's what it's designed not to do.
Okay.
Yeah.
But
it will solve your saturation problems, or at least alleviate them.
Mm-hmm.
Yeah. I think the only thing that would kind of break it, as we talked about the other day, is if you have a proxies or things in the way where that's basically doing deep packet analysis, might affect it depending on where those boxes sit and where your actual issue of traffic is. So it's really hard to say yes or no on that.
Right.
So.
Well, yeah, there's no way to, it would be very difficult to detect LEDBAT other than doing some sort of TCP fingerprinting and looking at the amount of flow and say, oh, this is probably a LEDBAT flow, that one's probably a cubic, which is possible. But LEDBAT is a TCP protocol, so it will go from TCP endpoint to TCP endpoint. If you have a box that splits the TCP in the middle, well, that's going to be the LEDBAT endpoint as well. So that's the information that we have for you at this point.
Cool. No other questions? All right,
Okay.
thank you.
That was a great set of questions. Wow. Oh, we got some more.
Do both ends of the TCP connection need to be aware of LEDBAT, or just the server end?
Only the server end.
Okay.
Yeah, basically the end that's pushing
Good
the data.
question.
So if it's the client side, NDO side, it's the client that has it enabled. So it is in Windows 10 and Windows Server 2016.
Thank you.
Yeah, so in TCP speak, there is no server and there is no client. We have senders and we have receivers. So the sender side has the congestion control protocol or algorithm, and it controls how much data is sent. Leadbat is a congestion control algorithm, so it's a sender side algorithm. Typically, a server is a sender because it's sending data to the client, but a client can also be a sender too in an upload case. Does that help any?
Yeah. Are there any plans to retrofit this into the older OSs like 2012 R2 or even older?
Yeah, that would be really difficult, next to impossible, because the infrastructure that allowed us to build Leadbat is not in those operating systems. Basically, it's pluggable congestion control. We built that into WS 2016, and then we started adding new congestion control protocols, and it doesn't exist prior to WS 2016.
Okay, thank you.
You're welcome. Anybody else? I can't really see because of the lights. Okay, thank you guys very much. We really appreciate you being here. You've been a great audience, great questions, and it's a great Ignite conference.